Eigenvectors in low-dimensional dynamical systems are not very interesting. In low-dimensional dynamics, the trajectory is a one-dimensional curve being traced out by the system in 2 or 3 or some number of dimensions, 4 or 5. It has one obvious eigenvector, which is the velocity at the point along the trajectory or tangent to the curve. That's a marginal eigenvalue for long-time orbits and for periodic orbits and relative periodic orbits. And then it has some unstable eigenvectors and some stable eigenvectors. And the number is the dimension of the system, and they don't look very intuitive or very interesting. However, when you look at linearized stability of hydrodynamical flow or spatiotemporal patterns of some dissipative system, the eigenvectors are actually very intuitive, and they give you lots of information about the flow. Let's take as an example cardiac dynamics in two-dimensional plane. If we assume that this plane is very large compared to characteristic scale of the system, then the obvious eigenvectors, which are the marginal eigenvectors in which you perturb infinitesimally your pattern in such a way that you shift it either along the x or y direction in Euclidean plane, or you rotate its phase, they're quite informative. First of all, they're concentrated on the shape that you're interested in. So they look, if you're looking at a spiral, these eigenvectors also look like spirals. But if you sort of color code them to see whether they increase or decrease the solution that you're looking at, they will have edges in direction where you are moving the thing. In that direction, in the front edge, you'll have an increase. And in the back edge of the figure, you'll have a decrease. And if you're looking at rotational motion, in the front of the direction of rotation, you'll have an increase, and in the back, you'll have a decrease. If you're looking at perturbations of several localized structures in the plane, then each one of them will have its own eigenvectors, and you'll be able to distinguish what are you perturbing just by looking at the eigenvector. There'll be some two-dimensional state of the system which will tell you that the perturbation is moving one of the structures around. The expanding and the contracting eigenvalues are also much more intuitive than they are for low-dimensional systems. You can think of it just as the way you think of deformations in elasticity theory. The expanding eigenvalues will have to do with some deformations which are now not translational. They're intrinsic to the coherent structure, in which the structure goes unstable. So maybe you squash it in some way and it turns out in linear approximation that squashing actually can continue. And there will be translational kind of things, so that your pattern will look like it's ringing when you look at these eigenvectors. There might be rotational ones, then it'll look like it's rotating. It has some rotational form. And the dissipative eigenvalues, the ones that contract, will also be similar, and the leading ones will have some similar structure. They'll tell you that if you the eigenvectors will be organized by increasing number of wiggles in them, just as they do in elasticity as modes of a drum or in quantum mechanics. So there'll be some deformations, maybe there's an elliptic deformation of your circular pattern, which dissipation doesn't like, so it will oppose it. So the eigenvector will again be concentrated on this figure, but from it you could tell what kind of eigenvector it is. As your pattern is in an infinite dimensional state space, it's a function defined over the two-dimensional plane, and then you'll have infinitely many eigenvectors. And so far I've argued that the leading ones can be easily understood. And it's extremely important to look at these eigenvectors to understand the nature of stabilities and instabilities of your solutions. Also, the very high ones will be, in some sense, trivial. If you have something that has infinite extent, the high ones will really correspond to high Fourier modes. Because if you impose a high Fourier mode, that's an eigenmode of your geometry, of your translational invariant system. But dissipation will kill it. It'll decay very fast. So these high eigenmodes will just look like, Fourier patterns, numbers of wiggles in this or that direction if you're looking at a rectangle, or some kind of angular wiggles if you're looking at the angular motions. And they'll be mutually orthogonal because, Fourier modes are orthogonal. So while the leading eigenvectors are very non-orthogonal, and that's the important part of what we're trying to explain, along the leading instabilities, you can actually get entangled with other features of the attractor. These very high eigenmodes will be, quickly damped, and they'll have no awareness of the structure they're looking at, because they'll correspond to high frequencies where these structures, don't contribute in any meaningful way.